Hello and welcome everyone to my new video. Today we will start magnetism. Now, to understand magnetism, let us first understand the two conditions in which a charge can exist. A charge can either be at rest or at motion in given particular time. If it is at rest, we must understand that it only produces electric field, while when it is at motion, it can produce both electric field as well as magnetic field. The second point is that a charge carrying conductor only produces magnetic field. The third point is a law which governs almost much of magnetism, which is known as Biot-Savart law. Now, what is Biot-Savart's law? To understand Biot-Savart's law, let us consider an arbitrary conductor with current I flowing through it and consider an element of width dl. Now, for this arbitrary conductor, a current element is defined and value of current element is I dl. Now, what Biot-Savart law gives us is the value of magnetic field at any point P which is situated at a distance r from this conductor. We can write Bp is I dl sin theta upon r square. In vector form, the B vector at point P can be written as I dl cross r upon r cube. The fourth point which is to be discussed today is magnetic field due to motion of charge. We must understand that, as discussed before, motion of charge can produce both electric and magnetic field. But in today's scope, I am only going to discuss magnetic field produced by a moving charge. As you can see, current element in this situation is defined as ideal. But in case of a charge q, let's consider a positive charge plus q, which is moving at a velocity v in a magnetic which is moving at velocity v. Now let us consider a point P at a distance r from charge plus q. As you all know, the plus q can produce magnetic field at point P. We will discuss about the direction of the magnetic field later. So today let's concentrate on the values of the magnetic field. The magnetic field B at P can be given as mu naught by 4 pi q v sin theta upon r square. Now this magnetic field, as you can see, is very similar to what is produced by a current carrying conductor. The only difference is that the current element in this particular case was ideal, but now it is QV. We can also write the vector form of this magnetic field as mu naught upon 4 pi q v vector cross r vector upon r cube. This is the magnetic vector. We can write the direction as r cap. Okay. Now, this QV is known as equivalent instantaneous current element of a moving charge. In this case, it was ideal, and in this case, it is QV.